Good evening. Good evening. Can you hear me? Okay. This is also serving as a mic check for our speaker. My name is Jordan McGee. I am Director of Education here at the National Atomic Testing Museum. So many of you have been to all of these events this year. Thank you so much for coming. That also means you've heard me do this introduction of myself a dozen times already. So thank you. And as always, on behalf of our entire staff and Board of Trustees, I want to welcome you and thank you on their behalf for spending your evening with us. Before I introduce our speaker this evening, I have a quick announcement to make. I am really thrilled to finally unveil the first edition of the 2018 Distinguished Lecture Series. Some of you already have the flyer. If you did not grab it on your way in, please grab one on your way out. It looks like this. It has a whole lot of white space on it because I am in the middle of finalizing several other events for 2018, so expect that to grow, particularly in the back half of the year in the late fall this time of year, but the front half is pretty well solidified. Our first lecture of 2018 will be on January 26th, Friday evening as usual, and that will be a panel discussion on the 40th anniversary of Operation Morning Light. If you are not familiar with what that was, 40 years ago, a Soviet satellite crashed down into northern Canada with its nuclear power pack still attached. I'm saying this in very simple, non-scientific terms, and scattered radiation all over. And a team from Nevada was sent up to remediate, help clean that up. And it's a really interesting story that combines science and history. So you'll get a dose of both. Ha 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 ha. So please plan to join us for that one. And I hope you're all as excited about the others we have lined up as I am. I think we're going to have a really good year next year. However, on to tonight's lecture, which I'm really, really excited about having this as the final lecture of the year. The topic of radiation is one that we get asked about very frequently here at the museum, and it's a complex one to unpack. Our new radiation exhibit is actually being printed and mounted as we speak, and we hope that it's going to demystify some of the basics of radiation in the world around us when it debuts in the next couple of weeks. And that exhibit, by the way, is going to be on that wall, which is now nice and blank and ready to receive it. Of course, it will be in our e-blast when it's ready to go. I'm hoping by the time you all come back in January for the next lecture, it'll be there for you to see as well. But that exhibit's going to change and evolve over time to cover many topics of radiation, from famous accidents like Chernobyl to important medical applications. And we'll continue to offer lectures that complement the overall themes presented in that exhibit, the first of which being this lecture tonight. So tonight's lecture topic, the radiation risks for space travel, is one of particular current interest as we continue to see talks of travel to Mars and beyond in the news and current events. It's kind of all over the place. So we're really, really fortunate to have one of the most knowledgeable people, I think, on the whole planet here to talk to us about it tonight. Dr. Frank Cucinotta joined UNLV's Department of Health Physics and Diagnostic Science during the fall of 2013, and he teaches radiation biology, radiation dosimetry, radiation science within the undergraduate and graduate programs. Prior to joining UNLV, he led a team at NASA focused on the potential radiation health risks to astronauts visiting Mars and determined how to mitigate those risks. He was president of the Radiation Research Society during the 2013-2014 years and is a council member of the National Council on Radiation Protection and Measurements. He has been published in more than 350 peer-reviewed journals and articles and written numerous book chapters. So I'm not kidding, he's totally the best guy around to talk about this. So please join me in welcoming Dr. Frank Cucinotta.
Okay, thank you. Thanks for everyone coming, and especially Jordan inviting me, and the other people here at the museum. I see I already have a typo. I put bomb in my title for the museum, but I guess it's like MRI and MRI. So I would talk. The talk, I have to talk about risk and risk perception, and that will be mixed with the environment in space and then talk about the actual health risk and how the problems we have in estimating them. So some people think the risk for going to Mars are too high, and then some people think we'll just dismiss the risk. It's like, are you a soldier or a saint or a martyr? Or you are a government employee. So there's different perceptions of risk. And the main problem is we really don't know the risk. So before we can say it's too high or too low, we really need to understand the risk accurately. And then someone in policy world can decide whether it's too much or too small. But I'll talk about what the standards are today. Okay, So I think this audience knows what ionizing radiation is, but I put this in just because, just in case you think about UV. So we're not talking about UV or other types of things that go with the word radiation, but want to focus on ionizing because it's a different type of radiation. So all biological effects and health risks from ionizing radiation is due to ionizing the atoms in the molecules like DNA or the water near DNA or proteins in a cell or in a tissue matrix. And what's different about space radiation is it includes high LET, high linear energy transfer, meaning the patterns of ionization are different. So there's going to be a quantitative difference, but also a potential qualitative difference, that it ionizes in a way that X-rays or gamma rays can never do. So that could lead to some things like types of DNA damage that X-rays and gamma rays would not do until you got to, say, 1,000 gray, which is 100,000 rads. So it's not really interesting because you're fried at that point. But within one region of a chromosome, it can put so much ionization in there that you just can never get that with X-rays or gamma rays or low LET radiation, we call. So we'll talk about the patterns of radiation. And just to remind you about the units, because some of my slides will have the units of dose and the biological dose, what they call dose equivalent. And there's a whole jargon for that, just to try to keep it simple. So the absorbed dose is a macroscopic quantity. It's the amount of energy per unit mass. So joules per kilogram, and that's given the name of gray. And then the older unit is a rad. So 1 rad is 0.01 gray, or 1 gray is 100 rads. And then they have a fudge factor called the quality factor that tries to take into account the different types of radiation, which is very important for space radiation. So they call the older term is quality factor, and NASA still uses quality factor, but the International Commission of Radiological Protection, the ICRP, uses a radiation weighting factor, which is a little bit different. And then you take the gray and you multiply by the quality factor, and for that type of radiation that you're interested in, that gives you the dose equivalent, and you add a specific organ, and they have a method to sum it over all the organs that's used in radiation protection on Earth to give you the effective dose. So that would be in the units of sievert. So then there's different ways to apply that, and I just want to keep it simple. Okay, and then so you have all these other definitions, but we won't need to talk about that. Okay, so just talk about the microscopic energy deposition. So this is protons. So I'll get to the environment. The protons are in space, but this is a high energy protons or low LET radiation, and they're going to be similar to X-rays or gamma rays that we're familiar with on Earth. So what this graph shows you is a computer simulation of each dot is an ionization, and this is a box that's 5 by 5 by 5 microns. So it's bigger than a mammalian cell. And so each one of those dots is along the track of a proton. And if you look at that microscopically, it's going to be quite different. So then you start to say, well, I need to average this out over a volume. And so we know which volume you want to look at. So the absorbed dose is macroscopic. It's an average over a big bulk material. But if we start saying, bring in the scale and then average over 20 nanometers and then 40 nanometers and go up in the scale, you can see there's going to be hot spots as you go through the smaller volumes. So this is showing now not the macroscopic dose, but what we call the microscopic dose. It's the energy deposited per unit volume or per unit mass, but the mass is very small. So you have a ratio, energy divided by mass, and now you have a small mass, so that blows up the dose to very high values. You can see if it gets up into the red, it's 100,000 gray in that small voxel. So quite different. So this would be simulation of 1 gray in the box, And to get 1 gray, if you know the formula for dose, it's the number of particles times their LET, how much energy they deposit or transfer. And in this case, for 300 MeV protons, which would be typical in space, you would have 450 protons go through the box. And that would give you a dose of 1 gray. And then if you average it out. So now if you go up to a bigger voxel, it's going down to that 1 gray. And if it's a smaller voxel, you'll get some hot spots. And you'll get some voids where nothing happens. There's just black and no ionizations occurred, no energy's deposited there. Okay, so now go to a high LET radiation. This would be an iron particle. And I'll show you in a little bit that cosmic rays have different heavy ions, and iron is the one that is the heaviest one that has a high abundance. So we look at this a lot in experiments at particle accelerators. And this would be to get 1 gray in the box, 5 by 5 by 5 microns, you just need 1 particle. So 1 particle gives you 1 gray, but you can see there's a lot of empty space, and now you see the track is this, this is where the particle went, and there's this what we call the core. And then what's coming off the core is secondary electrons that we call delta rays. So there's a few lower energy delta rays, and then there's some. And actually, some of these delta rays can go out like a centimeter from the track. That they come off with so much energy. They're not really that important. It's the ones in close that are important. They'll do the same thing and start averaging it over voxels. And now you can see that you have a big red streak. So that would be the qualitative difference. That red streak might cause ionizations to DNA or other biomolecules, which are going to be on order of tens or a few tens of nanometers would be a typical biomolecule. So the number of ionizations you can get in that molecule is just completely different than X-rays or gamma rays. You'd have to go up to, like I said, 1,000 gray of X-rays before you can get that many ionizations so close together. And then also the averaging doesn't work. So you're up to 160 nanometers, still lots of empty space. You go up, and then so you have to get up to about 260 nanometers before it looks like 1 gray. So the absorbed dose doesn't work too well is the one point. Okay, so now the environment in space is going to have solar particle events. These come from the sun. Trapped radiation, this is the Van Allen belts, the radiation that comes, interacts with the Earth's atmosphere and the magnetic field of the Earth and gets trapped. There's a proton belt that the space shuttle and the space station now go through. That's a few hundred kilometers up to a few thousand kilometers, and then there's a higher altitude electron belt that also dips down in some places to lower altitudes. And then there's the galactic cosmic rays, and that's the one we're most concerned with. We'll show you in a few minutes that you can't really shield the galactic cosmic rays. Their energies are too high. The solar particle events you can shield. So that you have to have the wherefore, which means real-time dosimetry to know to shield it. But you can shield it with not too much material. Okay, the environment, let's see. Just a little bit more about the environment. So where does it come from? So the idea is that the galactic cosmic rays come from supernova. So they originate the stars. They're emitting solar particle events. And there's also supernova explosions. And there's processes that accelerate particles to very high energies. And there's also fusion processes where you form heavier nuclei from the fusion of lighter nuclei. And we'll show you some examples. But you can shield it, but it's just too costly. For example, our atmosphere is equivalent to about 10 meters of water shielding. So that does it. So if you have 10 meters of shielding, you're safe. When you get down to the ground, you just have the remnants of these heavy ions. And even 5 meters of shielding would do a good job. But 2 meters of shielding doesn't really give you too much advantage. You might cut it in half with 2 meters of shielding. So you really need a lot. And then if you think about how much does it cost to launch mass into space, it's about $1 million per pound. So unless you have other uses for that material, and then you also have competition for the rockets to launch other things into space. Okay, so it's really a biological problem. It is the dose that you get from these cosmic rays going to cause risks that are unacceptable. And because of this qualitative difference, due to the ionization patterns, are there going to be effects that we don't understand? What about epidemiology? So with X-rays and gamma rays, we have the atomic bomb survivors in Hiroshima, Nagasaki, and we have medical patients. We have studies of reactor power plant workers, so we can understand to a pretty good extent what happened to them, but this is a different type of radiation, and there's just have not been enough astronauts in the past, and their doses have been relatively low and short emission, so epidemiology doesn't do too much for you. So you have to really use an experimental approach to understand what the risk would be. And so that's lots of other things that you have to think about. Does a mouse represent a human? I won't have time to talk about it. And in some extent it does, in some extent it doesn't. Okay, then solar particle events, their energies are high, but not that high, and we'll show you, you can shield them, so I'm not going to talk too much about them. So these are typical cosmic ray spectrum, different heavy ions. You can see there's iron, silicon, these are the major ones, oxygen, titanium. And then if you think of, if you're familiar with the concept of a range, the range is the average distance a particle will go in a material before it stops. So when you get up to this higher energy part, you're talking about hundreds of centimeters of water before you can stop it. And what will happen is, rather than stopping it, you'll have a nuclear reaction. So these also are high energy, they'll have nuclear reactions, and you'll break up. So this iron particle, after a few interactions, nuclear interactions, it will break up into protons and neutrons, and you'll produce electrons and ground level muons and things like that. So after a few mean free paths, and the mean free path is about 10 to 20 centimeters, depending on the energy, you're going to break it up, and then you keep breaking it up into lighter and lighter particles, and that's why we don't see it on the surface of the Earth. These higher energy ones, you could get it through the atmosphere, but they'll fragment into protons and neutrons and other things before they get to the surface of the Earth. So, and this also shows you the modulation. This would be the spectrum outside our solar system, and this would be how the sun modulates. So it modulates the lower energies, but not the higher energies. So the solar wind and the field of the sun, and the solar cycle is about 11 years. So you have a varying solar wind over that 11-year cycle. And then this shows you the effects of the reaction. So this would be what's called the Bragg peak. This would be the range when it gets up to this peak. So as the particle slows down, it's slowing down because it's ionizing. Every time it ionizes, it loses a little bit of energy, an order of 100 eV. So these would be thousands and thousands of ionizations as it goes through material. Then eventually it stops. Right before it stops, its energy deposition, or its LET, goes to a peak, and then it falls down. But you see what's going on is this is the beam produced at a particle accelerator, and this is all the secondary nuclear reactions that were made. The lighter particles that are produced in a reaction will tend to have a higher range, so they'll go way up beyond this Bragg peak. If you went to a lower energy beam, the tail would be very short. So this is a spin-off would be, this is what's used in cancer therapy with protons. You can have a proton beam that's peaked at the tumor. So depending on the depth of the tumor, you change the energy of the beam. So the dose is maximum in the tumor and lower in the normal tissue. And in Europe and China and Italy, they'd use carbon beams. And the US hasn't gone there yet, but they have some advantages for treating tumors. But the Bragg peak is the reason for that. But you wouldn't use these heavier particles for treatment because this tail is so large. Then if you went up to the higher energies, you would no longer have a Bragg peak. You would just have an exponential decrease because of the influence of the nuclear reactions. So this shows you what happens for shielding. So I don't have time to talk too much about shielding, but just to show you, this would be shielding and where we've taken into account the body shielding that's behind different amounts of material. So this is showing for aluminum and polyethylene to show you the difference. So aluminum is the standard material that's used in spacecraft, and then polyethylene would be an alternative. The best material turns out to be hydrogen, so not lead, the exact opposite. You want to use hydrogen shielding, and that's because you have these three processes: the slowing down, the nuclear reactions from the beam, the projectile cosmic ray, but also the nuclear reactions from the thing it's hitting. So if you have a heavy material like lead, when these cosmic rays hit it, it knocks a bunch of neutrons out. So that's bad. So hydrogen, you don't have much neutrons. There's some exotic phenomena at higher energy where you can make a neutron, but it's relatively rare. And then you have the slowing down. The slowing down goes like the charge divided by the mass. So the hydrogen has a ratio of 1/1. The charge number is 1 and the mass number is 1, so it's most effective. Everything else goes down quickly to 1/2. So polyethylene is 6/12, a little bit less because a little bit more better than in the hydrogen. Aluminum 13/27. So everything else is down around 1/2. So hydrogen is the best. So it's the best for what we call the target fragmentation from the shielding, either the spacecraft shielding or your body shielding, and it's better for it turns out it's also better for the breaking up the cosmic ray, and it's also better for slowing down the material. So hydrogen is the best, and polyethylene's a nice alternative. But you can see what happens is at solar min, where you have the lower energy particles, you get a nice decrease, and then nothing. So there's another slope turning point out at about 2 meters. So the optimal is about here. So that's about 20 grams per centimeter squared. This is what's called areal density. So if this was water, the density is 1, so this would be 20 centimeters. And then it's just adjusted by the density of the material. And that's what we use in the aerospace world, because mass is the bottom line. And also a lot of the physics quantities go by the areal density rather than the physical thickness. And then at solar max, it's not as good. So because you don't have, solar max here, because you don't have the lower energy particles. So this part is the stopping from the atomic collisions. At solar max, you'd have less low energy particles, so you don't stop them. And then you have it can increase because the secondary radiation is too high. And you see, you do have a nice difference between polyethylene and aluminum, but polyethylene doesn't solve the problem. So you can go to a carbon composite. Polyethylene is actually flammable, so you can't use too much in a spacecraft. And you can't use liquid hydrogen, that's very flammable. So you're stuck with something like water and locations, but you can't make a spacecraft out of water, but you can have localized shielding out of water and a bit of polyethylene. So the shielding is not a solution. I don't have time to show you solar particle events, but their depth just goes right to 0 after about 30 or 40 centimeters of water. And it depends on which solar particle event, but that's the issue. So the problem is stated here that it's different types of radiation. You have the heavy ions, we call them HCE for high charge number and high energy. And then you also have low energy protons, which are high LET, and neutrons from the spacecraft or from your body. You make a lot of neutrons in your body when these cosmic rays hit them. So you have unique damage and you don't have any human data. I'll show you one example with cataracts where you do have human data from astronauts. So you have to go to models, so animal models and cell culture models to understand the risks. These are some old pictures of nuclear emulsions where the grains are due to the ionization. So you can see as you go from hydrogen up to iron, how dense the ionization pattern gets, because it goes like the charge squared. So iron is 26 squared. Okay, so a little bit about radiation protection and perception of risk. The older limits at NASA were 4 sievert limit, and that was based on the Apollo time frame. And what happened was that in the Apollo time frame, it was all younger males. They tend to be in their 30s, military pilots, test pilots. And also, the atomic bomb data was pretty fresh back then. So if you look at an epidemiology study, it's about a time lag of like 5 to 10 years from when they have the data to when it's reported out. And so the cancer risk in the 1960s was thought to be leukemia-driven. And by the end of the 1970s, they knew it was solid cancer-driven. The estimate of risk per unit dose in Hiroshima and Nagasaki tripled from the 1960s to about 1985. And that's driven by the people living out their lives and you're seeing all the cancers develop. So the leukemias come quick, they can come within a year. And the solid cancers, lung cancer, stomach cancer, et cetera, take longer to develop. Maybe you'll see it at 10 years, but it's really peaking at 20 to 30 years after you're exposed to the radiation. So the estimates went up. So that's a pretty high limit. Other things have occurred where they re-estimated the organ doses of the atomic bomb survivors several times, and it fluctuated. One of the things was the amount of neutrons in the Hiroshima and Nagasaki bombs was estimated to be lower in the last couple of assessments starting in 1986. And so if the neutron component is lower, that means the gamma rays are more effective. And so that also drove up the risk estimates. And there's other things they're learning about now where they see, in about the last 10 years, that they also see heart disease increased in the atomic bomb survivors. So it comes later in life, the heart disease. So they see that. Okay, so then in the 1980s, NASA had the space shuttle program started, and now you have older astronauts and also female astronauts. So they had a reevaluation by the National Council on Radiation Protection and Measurements. And this gave a new type of dose limit, very different from what's used on Earth because they're going to be sex dependent and also age dependent. And they came up with, well, how do you say what's your limit? What's your acceptable risk? So things like vomiting, death from radiation, nothing's acceptable, zero acceptance. And it turns out not to be very important. I know people know that radiation was discovered in the 1890s, and there's only been about 500 cases of acute death from radiation that are known. So it's not something that happens very often. Sickness occurs in normal tissue effects from in cancer therapy, where they get very high doses, but acute radiation death is really rare. There's probably more people died in the Hiroshima and Nagasaki fire in the fires that would have got acute radiation sickness and death, but other things caused their fatality. So they came up with the idea that you have a 3% limit. So that's the perception, is 3% too high or too low. How they came up with that number is they looked at what are called the safe, the less safe, and the unsafe industries in the 1980s. This was a 1989 report, and they said that astronauts back then had unsafe industry of going into space, the rocket launch, et cetera. And so they want this limit to be like the less safe industries. And then the second argument was the benefit of space travel. So that's the other part of it, setting an acceptable risk is the benefit of it allow you to take the risk. Okay, so that's where they come up with this 3%. And then they back calculated, depending if you're a male or a female, what dose would give you a 3% fatality risk, and then also your age dependent. So females have a higher risk for the same dose as a male, as far as the epidemiology says, and that's because of the three main reasons: breast and ovarian cancer, obviously, but also in the atomic bomb survivor data, which is still the anchor to all these risk estimates, lung cancer per unit dose turns out to be a lot higher. And that one's really suspect whether it's true, but that's how it works out. There could be something else going on there, but you're stuck with that model right now. Okay, so is that high? Is that 1 in 33, 3% risk high? So people worry about risk at launch. Okay, so now we're stuck with the Russian program, collusion with the Russians on launching, since we don't have a U.S. launch capability for about 8 years now. And then you all have all these other challenges for a Mars mission. So, what is the risk for the vehicle to blow up or not return safely? So there's been 3 accidents. One is the Apollo fire, so that's on Earth, and then there's the 2 shuttle accidents, and they were all human error. You can trace them back to human error. So so there's this number of what's your risk prediction is theoretical. So you can theoretically predict what's the probability that a given vehicle will fail. And just like for the human, you're making a prediction. So the predictions are now that it's about 1 in 270. That's NASA's prediction for the current missions, and they have advice from what's called the Aerospace Safety Advisory Panel, how to make that closer to 1 in 800 or close to 1 in 1,000. So it's driven by money. So you have all these issues, and if you remember the Mercury program, a year before the Mercury missions, that's the first NASA missions, those vehicles were blowing up on the pad. So it was very risky back then, but the big thing was the money. They put, and they still do big investments to make those risks small. So there's been no really engineering failures in a long time, not on the International Space Station program, and the shuttle ones, like I said, they were really human error type risk, type failures. Okay, so what about the astronauts? They're healthy workers. This is a little bit old from 2013, but you can see this is their survival curves compared to US males, and then never smoking US males, normal weight US males, and never smoking normal weight US males. And this would be the astronauts with the error bars. So you can see this is including the accidents and also some other accidents in airplanes that were related to their occupation. And this is where you censure them out. So they live very long. You can see the 50%, that would be the median lifespan, is not apparent. There's been about 4 deaths since then, 2 more cancers and 2 more heart disease, but they've also lived longer since 2013. So they're very healthy people, and they live very long lives, and they've had these past exposures. So why do they live long? It's not because of their cancer. They're, compared to the appropriate group, they're a little bit high, but it's not significant. These are the 95% confidence intervals, and this is the standardized mortality ratio. It's because of the circulatory diseases, they're very low. So relative to the US average, they're 3 times lower, heart disease deaths. And relative to a more appropriate population, they're almost significant, or not significant, but they're trending to a very low risk. Okay, so that 3% was in the 80s. If you follow it out, nowadays it's less than 1% in the less safe industries. So people keep improving their occupational safety. For probably most of us, the only risk we have is driving back and forth to work. But the less safe industries might be things like construction or fishing or mining. So like I said, the risk NASA estimates is 1 in 270. That's the theoretical prediction. The actuals now is about 1 in 200. It's a bigger risk, right? Because if the spacecraft blows up, the whole crew dies. Cancer risk, it would be unlikely that more than one would get the risk. And they say, but they're putting these big investments to drive that down. So the big thing is 1 in 33 is like 10 times higher risk that you're accepting. And for the Mars mission, people say, well, let's make it higher. The big thing is the detriment. So the detriment is how much life you lose. We're all going to die. So the detriment is how much life. So that's the next issue. Well, okay, 1 in 33, but less life loss. How much less life loss is it? So this would be some examples for gamma ray, equivalent gamma ray exposure. You can see it's varying up to 20 years. So this would be for people that are 45 years old. If astronauts that are 45 years old, the prediction would be that if they went on to get leukemia and die from leukemia, they would lose 23 years off their lifespan. And then it varies with the type of cancer. Now one issue is this is gamma rays. So I kind of feel 1 in 33, it's about 3 times more life loss than the vehicle blowing up. So it's about right. It'd be hard to argue higher. You can make other comparisons, like if you were in the Iraqi war zone, what's your risk? It's like 0.5%. So 3% is higher, and I think you might relax it a little bit. So the issue to me is, what is the risk? So that's the next part. Okay, so you have all these missions, and then the Apollo. They're all pretty short, right? The Mercury, Gemini, Skylab. Skylab was a little bit longer. Apollo, Soyuz, but none of them are the length of the Mars mission. Shuttle Mir, so the Russian space station Mir, up to 180 days. The space shuttle, typically 14 days. And then you also worry about EVAs. The EVAs, as a passing point, that the doses on EVAs are really low. because they're planned to be outside the Van Allen belts. So there's a series of orbits about 14 hours a day where you can avoid the Van Allen belts, and you can also avoid the worst parts of the Earth's geomagnetic field. So it's a tilted dipole, and there's a series of orbits where you can avoid all this. So the doses are pretty low. And then so this would be the actuals from a paper I did. This would be the TLD badge dose that they supposedly wore on their chest. A lot of them admit they keep it in the locker. And then this would be the estimate of the effective dose. And then this would be the estimate of a typical Mars mission dose, so a lot higher. And the issue would be, is that safe? What would be the risk for that Mars mission? Okay, so the safety requirements, again, are the 3%, but this theme I'm bringing up, it's a different type of radiation and means there's going to be uncertainty. So we went to a system where we not only look at did you stay under 3%, but we also look at the 95% confidence interval, and that's a secondary standard. You have to be under 3%, but at the 95% confidence level. Management can waive that part, but they can't waive this part. But part of the story is then to estimate that. And then there's also other limits for acute things, cataracts, developing a risk limit for cognition. That's like a hypothetical, but something that's being worked a lot. All these limits then determine your shielding dosimetry and other requirements, perhaps countermeasures. Okay, so this is the idea that if this is your central estimate, this is your 95%, this is your probability distribution that your risk could be any of these values, but it's weighted, and then you have to have the upper 95% confidence interval below the 3%. And if it's not, you can waive that, but it takes a secondary decision. Okay, so how do you estimate this is to look at all the different things that affect the uncertainty, the quality factor, dose rate, the epidemiology data, and then the risks that we're concerned about are cancer, central nervous system effects, and then there's a host of other types of tissue risks, cataracts, heart disease, and then there's the acute radiation risks. The uncertainties are the type of radiation, so the quality effects, the dose rate, epidemiology. Perhaps there's something going on with interaction with microgravity and space radiation. We don't know. And then how does people vary in their response to radiation? Right now, nobody knows how to do this, and there's something called GINA laws that prevent you from doing too much with that. That's the issue. So again, the solar particle events, this is a map of every solar particle event that we had since the 1950s. And this tells you the number of protons above 30, 60, and 100 MeV. And this is their range in water. So you can see these lower energy ones don't penetrate. This typical spacecraft will have a wall thickness of a few centimeters, but your body, the typical organ is about 10 centimeters down. And the average shielding in a spacecraft will be up near 20 centimeters of water equivalent. So these won't penetrate. So you're really talking about things higher than this. So it gets more sparse. And if you look at the doses, there's only a couple cases where you would go up to, so if you got 100, that's like 1 gray equivalent, in a few hours you could get sickness or vomiting, but this is for a lightly shielded spacecraft. And as long as you have a typical amount, and spacecraft will have a location with even higher amounts, you drive that down to a very small number. So you really have a way to say that this is a solved problem. You still have the issue about the dosimetry. You know, maybe something will go wrong, but otherwise you have a solution to this problem of solar particle events. How about cataracts? So this is the only epidemiology data on the astronauts that we see cataracts in the astronauts. So this would be comparing astronauts with a small dose to a higher dose, but either one is a very low dose, just orders of millisieverts. And you can see they're getting it very quickly after the mission. And this would be for ones with visual impairment. These would just be all cataracts. So the number one risk factor for cataracts is eye exams, because most of the time you don't know you have them, and it's only when you go to the optometrist that they tell you, because they don't do much. We all have cataracts in this room, but most of them are not visual impairing cataracts. So these ones would be. So you can see it comes up really quickly at these lower doses. So this becomes a question for the Mars mission. Would they come up to impair your vision on a 1,000-day mission at a higher dose and dose rate? So that's an ethical concern. I think some people call it Australian medicine. Maybe you would put artificial lenses in before you go, but that raises some ethical concerns. Okay, so that led to this picture I had that was in a news story for NASA. Have you heard about the twins paradox? So you have two twins, one goes to another solar system, and he comes back younger. So we say this is a paradox on the paradox, that actually radiation makes you older. So if you go into space, it's making Einstein incorrect. And so when we say aging, cataracts is an aging. A lot of aspects of cancer are aging, and then also cognitive effects would be aging, heart disease would be aging. So all these things are kind of tying into this aging story. So if these really low doses of heavy ions cause cataracts in the Apollo shuttle and NASA Mir astronauts, what else is it causing? So with X-rays, you wouldn't expect any cataracts up till you get to about 2 gray acute and 5 gray chronic. We would see really significant evidence of a cataract. This is from epidemiology studies. So we're seeing it at really low doses. So it's something different is going on. It's unexpected. It's not a quantitative difference, which is adjusted by the quality factor. It's adjusted. This is a qualitative thing that's occurring. Okay, so spaceflight, just to remind you, the missions, lots of missions being discussed, and then there's the Mars mission is typically 1,000 days, maybe 900 days. There's 2 types of missions they talk about: a conjunction mission, that's where you spend a long time on the surface, typically 18 months and about 6 months going and coming. And then you can do a higher cost mission that only has about 30 days on the surface. You get there very quickly. You can get there in 2 or 3 months, but then it takes about 15 months to come back. So the issue there is, on the surface, you have the body of the planet that cuts the dose rate down in 2. You also have an atmosphere. So every day on the surface is a little less than half the dose you would get in transit for the same day. So the people like the conjunction mission, but we have to balance out which one is more risky. So as part of this, a couple of papers that were in Science in 2013 and 14, so it turns out that cosmic rays were discovered by Hess in 1912, and the Mars Science Lab landed on Mars in 2012, so exactly 100 years later. And on the Mars Science Lab is a radiation detector. So this is the first time there was a detector putting on the surface of Mars. So this is the rover, and this is where the RAD, radiation assessment detector, is located. And they make a big deal that this is the first time that it was done. And there was 2 papers in Science. One was about the doses on the transit, but to me it was kind of like all predictable, because it turns out that the radiation outside our magnetic field is the same here as it is at Mars, and it's been measured to death, but they made a big deal. And then the radiation on the surface, okay, well, that's different, right? But people fly detectors on balloons up in the atmosphere, and it's the same thing, and the material is a little bit different, but because it's the first, it was published in Science. And then when you look at the surface of Mars, you have to talk about the soils. When these cosmic rays that make it through the atmosphere hit the soil, if it's on ice or if it's on regolith, the dirt of Mars, it'll produce a different backscatter. You also have the atmosphere. So straight up, it's about 18 grams per centimeter squared of carbon dioxide, basically. And then on the zenith, it'd be very long distances that the particles have to go through. So you can make a map that we published of, depending on the altitude and relative to the surface of Mars, how the exposures are changing. And then we made some predictions. So you can see the models predict very well the measurements either on transit or on the surface of Mars. And you can see it's about a factor of 2. The solar cycle's changing as these things go, so you have to adjust for that. But it's about a factor of 2, just like we expected. There's something interesting about the daytime, nighttime. As the atmosphere cools down, it changes the doses a little bit. So but it's like a 5% effect. But that was also reported in some papers. Okay, so the cancer model we do at NASA, again, it's different than what's used on Earth because of the type of radiation, but also because of it's a specialized group of workers, not just anybody. So we brought in quality factors for solid cancer and leukemia. Our baseline is never smokers. We use the atomic bomb data, but there's incidence data and mortality data. We use the incidence data and then convert to mortality using the conversion rates for the modern US population. That has to do with the changing cure rate for cancer with each decade. So this is predictions in the conventional model for these different types of missions. So you can see the confidence level can be 10% for males and up to more than 10%, 12 or 13% for females for the Mars mission they like. So that would be unacceptable. You're 2 or 3 times higher than what would be acceptable. And then the other thing that's interesting, so you break down the tissue, is they say, well, you're going to get cancer anyway. So there's something called probability of causation. I don't know if you heard about that, but that's the probability that if you got cancer at a certain time after your exposure, it was due to your radiation. So that takes into account your background rates of cancer. So this is the PR nightmare. So this would be 10 years. It doesn't really change after about 25 years. After the mission, you can see leukemia. If somebody comes back from Mars and they got leukemia, it's like 60% probability it was due to their radiation. So you can say, well, it was worth it to go to Mars, which one point of view. The other one is, why don't you mitigate this before they go, just like they mitigated the rocket ship blowing up. Make the right investment. So that would be the main points of view on this, and this is for males. Same things, different types of cancer would have high causation, and things like prostate, where you have a big background, would have low causation. Okay, so the other thing about cancer is the types of cancer seem to be different when you look at gamma rays or background in mice. So the spectrum of types of tumors you get with heavy ions is different than gamma rays or background. Also, the rates of metastases are different. So you can see that the heavy ions cause much higher rates of metastases, and they cause more invasive types of, in this case, colon cancers than protons or gamma rays, or also the spontaneous tumors. So that's another issue. The last part about the cancer is the non-targeted effects. So even now, they don't really know how cancer is caused. So what you probably came in from your background thinking, well, you damage DNA and that causes mutation and that causes cancer. So that's called the targeted effects model. And if you use that model, as your dose goes up, your risk goes up linearly with dose. Maybe at really low doses there's a threshold, but you're at a higher dose, so you don't worry about any threshold. And then, so the mission length is proportional to your dose. So you have this type of model. This non-targeted effects model says that cancer is caused by the damaged cells sending signals to the cells that are not hit by the radiation, or that the damaged cells cause the tissue to change, and then you get a different type of response to further aging or further radiation exposure. So you get a different dose response model. It's not linear. It's more something like when you smoke cigarettes. If you smoke 2 packs or 3 packs, it's not going to make a big difference. So there's a increase, and then it kind of just saturates out. So how radiation is causing the cancer could change the dose response curve. So this would be an example where if you look at higher doses, this would be chromosome aberrations for different types of radiation. It looks linear, but if you look at just the lower doses, you start to see a structure to it. And so this would be a sign of a non-targeted effects. So it turns out every study that looks at the lowest doses sees some other type of response, not a linear response. So that's bad news, because in space, you're down in this dose range where not every particle is getting hit. So this is another way to present that data, is take the y-axis and divide it by the x-axis. So if it's linear, you would get a straight line, but if it's non-targeted, you'll get a increase. So this would be the conventional model. You take the y-axis of the previous slot and divide it by the x-axis, and you get a straight line. But when you get down to less than 1 particle, so not all per cell, not all the cells are getting hit. There's bystander cells that are not getting hit. You can see it goes through the roof. So that means there's a hidden part of the risk if this is true. We don't know if it's true, but all the experimental models suggest it's true. And again, we don't have human data. So this would be how the prediction for a Mars mission would change. You would double the risk when you have this non-targeted effect, and you would have a different shape as you go along and extend the mission length. So all this kind of says that the cancer risk, the fatal cancer risk, would be about 10% or less. The mean would be probably less than 5%. So that's probably acceptable. You know, the beauty and the one-of-a-kind thing of going to Mars the first time would probably allow the United States or other countries to take this risk. But if these other models are correct, then it becomes that it could go up to 20%. So now you're talking about a Russian roulette type of mission. So maybe that's not acceptable. So my point of view is, well, somebody else could decide what's the acceptable risk, but you need to know if this is true or not, because you can't really make a good judgment without knowing that. Okay, so in the last 5 minutes before we stop, I want to talk about the cognitive effects of radiation. So this is a newer one that people are worried about. You wouldn't expect it again from people exposed to gamma rays or X-rays at lower doses, that we're talking about a few gray or less, that you would get cognitive effects. Okay, but there's some newer evidence in animal models that you do see these effects at lower doses of heavy ions. So there could be an acute part to this and also a late part. So the late part, maybe it's going to accelerate dementia would be the idea. So you know that in the aging population, about half the population will get Alzheimer's if they live to be 80 years old. And so what we would be worried about is if it comes pretty late in life, unless you have a genetic susceptibility where they call it early onset Alzheimer's, and Alzheimer's is about 80% of the overall dementia. There's other types of processes that lead to dementia. Would you push that up earlier in life? So instead of getting it when you're 80, you get it when you're 60 because of your space radiation exposure. So that's the worry. And then this one, but even more important, could you not operate the vehicle or perform the mission? So the camp that says, I don't care about the cancer risk, can't dismiss this, because they're kind of saying that this is like a wartime scenario. I got to do the mission, no matter what the risk is. But if the risk from acute changes to cognition and memory are too high, then they won't be able to perform the mission. So this becomes a big focus in the last few years. Okay, so the CNS risk, or this movie from my postdoc, Marat. So they're concerned, and what we would expect is that it's not a mutation-driven thing. So mutation-driven things are expected to have no threshold and just increase linear with dose. But these type of things to your brain and neuron cells are just, you're not really familiar with it. At very high doses, like very sad, people with glioblastoma, a form of brain cancer, they get such a high dose that they have all kinds of cognitive effects, but they're getting 60 or 70 gray to different parts of the brain, and they try to reduce that, but and then even then they have very low cure rates. So it's a whole different type of damage that you're occurring. This is going to be more subtle damage when we're talking about a Mars mission dose of a half a gray or a solar particle event of, say, 0.1 gray. So very low doses, what would you expect? So if they do see these effects at lower doses, what's causing it? Okay, so what they're seeing is loss of cells, and then oxidative damage that's persistent. So persistent oxidative damage is a culprit in Alzheimer's disease and a lot of cognitive changes. So you see that at fairly low doses of heavy ions, but again, it's going to be in mice and rats and not humans. So you have to understand, make the difference, make the thing. So these are some of the mechanisms, the changes to the support cells. So the brain has neuron cells, but it has other support cells, the vasculature and the glial cells. Neurogenesis, everyone knows that they've discovered that you make new neurons in two parts of your brain throughout life. One is the hippocampus, and the hippocampus is responsible for controlling your new memory and your spatial learning. So the new neurons are made, and radiation has been shown to impact that at fairly low doses, that neurogenesis process impairing and stopping the development of new neurons. The other one that I have a grant now from the NCI, National Cancer, is the morphology of the neurons is changed at low doses, and then persistent inflammation would be probably tied to these other mechanisms. So these are the mechanisms. This is an example of the mouse hippocampus. So they're big cells. So a typical cell nucleus is about 5 microns in radius. The dendrite on a neuron goes out to about 100 microns. So it's a big target. And then your memory, who you are, is located on these dendrites, right? All your synapses are there. So you're aware of some that you might change some of your synapses. So, and then there's the axon, so that's the output and the input to a neuron cell, so all the electrical, chemical processes. So people are worried, are these things changed by these low-dose heavy ions because of their unique ionization patterns? So here's an example of data, and they've shown this in the cortex, but also the hippocampus. So this is in mice, and you can see this would be these dendrites where all your synapses are, and they're called spines before they make the synapse. And you can see these are at 5 and 30 rad, so 0.05 and 0.3 rad. So this is definitely in the range of a Mars mission. You're losing the number of spines, and you're also losing, changing the density of spines. So these would, and then they can show that these things are related to cognitive changes in the mouse. Okay, now when they say show, it's a little bit an association, not really a correlation. So that's one of the major obstacles in looking at these cognitive and memory changes, is to try to find a one-to-one correspondence. So you can look at these changes and plot it versus the training of a mouse. So you're familiar, like water maze, time on a wire, and the spatial learning. So they have all these tests of a mouse to see that there's effects to different parts of the brain. So you can plot this versus that, but you could plot something else versus that. So you really don't know what's the cause and the effect for these things. It's much more complicated than things like mutations. So in biomedical research, you can mutate a gene, and then you can inhibit the gene, or you can use silence RNA to turn off the gene, and then you could put it back on. So there's more powerful tools that they have to understand the effects, and they really don't have the same tools here to understand what is the real cause for the cognitive changes. But neurogenesis and these morphological changes are definitely the main culprits, or the main avenues being pursued, along with persistent oxidative stress and persistent neuroinflammation. Okay, so this would be a picture we did of a radiation track going through a mouse hippocampus. So you can see it's changing, it's ionizing a lot of places, and that's going to disturb the signaling, either the electrical or chemical signaling between the neurons. This would be a mixture of different types of radiation. And then this would be our model of how it works, that if you have high energy deposition events, then you can cut the dendrite, and that would lead to a reduction in the length of that neuron. So that the reduction could change your cognition or memory, or it could lead to the loss or the death of that neuron cell. And then for the neurons, there's different parts of the brain have different structures for these neurons. Some of them are very simple, and some of them are very complicated. The other issue is humans have about 100 times more neurons, but they also have several orders magnitude more spines and synapses than mice and rats. And I hope we have higher cognition. So the issue would be is there redundancy, and how does it work? They really don't know these things. It's kind of like the neuroscience is being discovered at the same time we're trying to investigate the radiation effects. So the basic how it works isn't really described at this point, while we're trying to understand how radiation changes what they're trying to learn. Okay, so countermeasures to CNS risk. So I don't know. Would you do brain transplants? I think it's too early. So it's the main focus at NASA now, is to look at these cognitive changes and whether they would really occur. But I'm skeptical. Even though I got a grant from NCI that's related to proton and carbon and X-ray therapy, and I still do stuff on space radiation and cognition, I'm skeptical that it's really going to happen in a human. I think there's something else going on that would prevent these things from happening. Now, my counter argument is the astronauts I met at NASA. They go up into space and they come back and they go into management. So I think there's some kind of, something's going on there. Okay, so let me finish. So to finish with a plug for research. So what's the value of research in this arena? So some people say go to the shielding, but I say it's really the focus should be on understanding what the risks are, how to understand all the biophysics of how radiation causes cancer and how does it cause possible cognitive or other health risks. So the issue, here's an example we did that we built this model of uncertainties. So we said the uncertainty is like 3 to 4-fold. So you have a central estimate and then your uncertainty is about the 95% confidence interval is about 3 times higher. So what would be cheaper, to put shielding to get that number way down or to lower the uncertainty? So we argue that it would be much cheaper to lower the uncertainty, make that number have a 50% uncertainty rather than a 3-fold uncertainty, and that would lower your risk. That would lower your limit because of the confidence. It would shrink to a very small number. Just a plug, where do they do this? So in the US, we do it at the Brookhaven National Lab, which this is a space picture of Long Island outside New York City. And this is the relativistic heavy ion collider where they're looking at Big Bang science, and then there's other accelerators there, and NASA has built this small one called the NASA Space Radiation Labs. So a lot of the results I showed are from there, but there's also in Germany, and Chiba, Japan has done a lot of work, and then there's new efforts in China. I've been in China a few times. They have a big effort now to understand radiation risk for the Chinese astronauts. Okay, so this would be the solution to the problem, would be to reduce the uncertainty. I'll kind of conclude. Shielding you can certainly optimize, making hydrogenous materials. Selection, we don't really know about that. So I put 50%, but it's hard to pick people. So the issue here is you're not picking from the general population. You're picking from people that are capable of being astronauts. So maybe if I had 1 million people, I can find the guy or the woman that's more resistant to radiation. But if I'm down to a few dozen people, it's unlikely that you're going to find that person's more resistant or more sensitive. Okay, so I'll end there to show you that research really is the idea. And because we have this uncertainty, we're using a different type of approach to radiation protection, which looks at the probability that we're incorrect, so this uncertainty bound. And that's what's been adapted by NASA, and that's really, a lot of that's due to my work, that we have this probabilistic risk assessment model rather than saying my effective dose is 20 millisieverts. We look at the range of possible risks. So it's really a risk-driven model rather than a dose-driven model. Partly because of it's a specialized group of workers, partly because of the type of radiation and the higher levels of exposure that people would have. So thank you. Okay, so I guess questions or? Okay.
So I'm wondering about when you explained the delta rays in the beginning of the talk. So in biological systems, is there any preferential pathway that those would travel along or propagate along?
Yeah, so actually the delta ray, all radiation acts through the delta rays. So if you look at a gamma ray or a photon, they go in and they ionize and they make an electron, and then they're ejected and it's like a cascade, they make another one. So the difference is the heavy ions can make them very close together. They can make thousands of them within 100 nanometers, while an X-ray is only going to make a few in that. So the things that would be different because of that clustering of the ionization would be like when you have DNA damage, you have single strand breaks, base damage, double strand breaks, and actually they're occurring in your body all day long. You have single strand breaks, base damage, and even double strand breaks. And but what's different is with ionizing radiation, they make clusters of these. So you'll have a base damage and a double strand break right next to each other, and that makes it harder to repair. And then with this high LET radiation, you might make several double strand breaks very close. So very close means within a few tens of base pairs, you can have multiple DNA lesions, and the cell has a hard time repairing that damage. So that's the main example people know about. But there's probably other things about the ROS that you make in the cytoplasm or in the tissue matrix that leads to different signaling. So there's some evidence of that, but it's less understood, I would say.
So it's more likely to travel along like a polymer of some sort?
You mean the like a solid state effect, you think?
Or just wondering if we need like a protein backbone or a DNA polymer?
Uh,
Jump from molecule to molecule, or?
The delta rays are just kind of dumb. They just ionize wherever they go, they ionize. But it just happens that there are clusters of them that will occur. So like if you have a low energy electron, it's going to stop with 1 or 2 ionizations. It loses all its energy and stops. And then that causes a lesion. The cell responds to that lesion. So it has repair proteins and repair protein factories. And in evolution, there's certain ones that work very well. They call it homologous recombination. And then there's other ones that are very error prone. So that's the start of the story of the DNA damage. But there's also this non-targeted effects, or non-DNA damage effects, where it's more like you have these chemical systems, and you're turning on different chemical systems because the clustering of the ionization is different, and how they are interacting together is, our bodies aren't, or tissues or cells are not used to that. So you're turning on unique chemical reactions because of this clustering of the ionizations.
In a trip to Mars, you're dealing with another environment, the gravity environment. Is there any indication whether is zero gravity going, the microgravity when you're there, the zero gravity coming back? Is that going to make the radiation better or worse? That's all I'm sure there's not a whole lot of data.
Yeah, so the ionization wouldn't be different. The DNA repair, they've done studies where they've brought, so if you try to do a DNA repair study with the background space radiation, it's very difficult, but they've done studies with a source of radiation and cultured cells, and it looks like repair is the same. We have other evidence. When I was at NASA, we had a program of biodosimetry where we would take chromosome aberrations measure chromosome aberrations by looking at blood samples before and after the missions, and that is a way you determine a dose. And that would be just what you would predict from ground-based measurements. But these things like the cognition could be different, because you also have other stressors like sleep, deprivation, the stress of the mission, and then the radiation. So the combination of those things are perhaps different. And then another one would be immunology. So the immune response is changed by the type of gravity and also by the stress. So that there's another interaction with radiation. But I don't think cancer would be, there'd be any type of interaction between microgravity, changing gravity, and the space radiation, because it's a not at this time. Not at this time. I think this has been reviewed by different select bodies, the National Research Council and NCRP. And on one hand, they're saying there's no evidence really to do that. On the other hand, there's probably not enough studies. That there should be more studies on this.
Thank you very much for that. I have one question, and I'm glad that you're talking a lot about DNA repair and DNA repair mechanisms. But I wonder how some of the data that you were presenting or that is shown, their extrapolations from Hiroshima and Nagasaki, where the radiation and the way that the cells get to respond to that type of radiation is very different than how the cells could respond to the similar dose in a more prolonged amount of time. How does that skew the results and the risks in one way or the other?
Yeah, okay, so that's a good question. So that goes back to the quality factor and the RB. So if you can measure, say you want to know lung cancer risk, so you have the atomic bomb survivor lung cancer data. That's actually a bad one because smoking. So let's pick one like colon. Colon cancer is a big one. That's a bad one because they get low colon cancer. We have high colon cancer. But you see, everyone has a caveat. But if you could measure, if you had a good model of lung cancer, say in mice, and you expose it to gamma rays, and then you have the gamma ray data for lung cancer and atomic bomb survivors, and you look at it, is it the same type of lung cancer, the histology of it, is the dose response similar? Is it a linear quadratic function or a linear function? So if you know all that, then you have a good starting point. And then you bring in the new type of radiation and you scale that to the gamma rays in your mouse, and then you adjust it by the human data. So that's basically the approach that's used. And then, so when you do that, then you can make adjustments for dose rate, age, chronic irradiation versus acute radiation. So, that sounds good, but the question is there enough data to do it? And in some cases there are, in some cases there not. Leukemia, it seems to work very well, but a lot of these solid cancers are not enough data.
You mentioned that you're not a huge believer in like shielding and those sort of things, and obviously more understanding is going to make everything work better. But do you have any sort of opinions on what would be a future remediation for the issue?
Okay, so I did say that for solar particle events, shielding is all you need. Because we see these people with crazy idea like active shielding and plasma shielding. You don't need that. You just need a few centimeters of water inside your spacecraft, which is already pretty bulky. And that will take and then you need a dosimeter to tell you there's a solar particle event, so you go into where that shielding is. So I'm a proponent of that, but for the cosmic rays, it's just, you just need too much. So to me, the bottom line is the risk too high or too low? If it's too high, then you would need to have a big program on biological countermeasures or selecting people. Both of those are problematic. First, if you had, like I mentioned, the story about the astronauts, you're not picking from the general population, you're picking from a pre-selected small group and then trying to find somebody who's has the right genes. So I think that's a problem. And then countermeasures, I think it's worth pursuing, but it's almost like, do you have a cure for cancer? And then there's no such thing as better and better treatments, but nobody's cured it. So, and then when you get into it, are you going to be lax about your standards, or are you going to be strict about your standards? So the example I give is, say, I have a 3% limit. My risk is 5%. I'm going to take a countermeasure to get below 3%. How are you going to prove that? It's very difficult. So, but now if you have a countermeasure that's has no side effects and no problems, you might just take it, so be lax, say, I'm going to take the 5% risk and hope this countermeasure lowers that risk. But now the research on the countermeasure is a problem too, because if you have a targeted effect, it might work. One agent might work, and if you have a non-targeted effect, you might need a different agent. And then if you have cancer risk, circulatory, heart disease risk, and cognitive effects, do you need a countermeasure for all three of those? Is there such a countermeasure that would work on all three, or do you need a different one? And then I guess to become like a typical American citizen, all kinds of pharmaceuticals. But it's different than patients. You have you're getting dosed today and you take some agent, but this is a chronic exposure, so that's the other issue, is you need some agent that you can take over 2 or 3 years with minimal side effects.
I have a couple quick questions. One, there was quite a bit of press a couple years ago on potential cognition effects due to the buildup of amyloid plaques. Do you think there's anything to that as a mechanism for potential cognitive effects?
Oh yeah, that was Kerry O'Banion at Rochester, I think, paper, yeah, in PLOS One, yeah. So they used an Alzheimer's mice. So these are mice. So Alzheimer's don't get Alzheimer's disease. Mice don't get Alzheimer's disease. So they can introduce genetic changes where they'll get the pathology of Alzheimer's disease. So these mice will get them like at 1 year. They'll get plaques, and then what they did is irradiate these mice and saw that the plaques came earlier in life. So that actually was something I was arguing for, that we needed studies on that, but it's kind of petered out. I don't know if it's true or not. They did 1 gray and 0.1 gray of iron particles, and they saw a really big effect at 1 gray and not really this marginal effect at 0.1 gray. The Mars mission total heavy ion dose is going to be a little bit less than 0.1 gray. So that's a mixture of all these different types of heavy ion. So it doesn't really say. More information is needed.
The second question is, there's been some research to suggest that with swap the cells over to glycolysis, radio adaptive pathway, which seems to have some sort of radio protective effect. Do you think there's anything to that and potential application there?
Yeah, I don't know. I've seen some of those studies. It seems like there's a window. It's not really proven for high LET, and it seems like there's windows where these things occur, but I don't know if they would be useful in a long exposure. And, the limitations of which cells they looked at, all these kind of things.
Looking at the difference between chronic exposure and acute exposure, can you talk a little bit about how the animal experiments are set up to try to replicate a more chronic exposure so that you get a more chronic response?
Yeah, so that's a problem. They haven't done much. People have done fractions where they do a fraction either once a day or once every 2 days for a couple weeks. So you can, yeah. Yeah, eventually they would, and the limit of chronic and the limit of infinite small fractions, they would be the same. So whether they reach that limit is the question, and they haven't studied it enough. So these are like expensive experiments. So the other way to do it would be to just have a low dose rate exposure over like a mouse. A Mars mission in a mouse is about 3 weeks. So if you did a 3-week exposure in a mouse and just and then let it run out. But the problem is that it's like $7,000 an hour at Brookhaven, so they haven't done that. They've just done this fractionation stuff.
I think it's similar to trying to say understanding dose relation to biological response from an acute event like an atomic bomb, and then doing the same thing with the mice. Because, like you said, we go through mutations, single strand, double strand every day, and our body has ways to deal with them. But then when you do something that's slightly different or too acute, then they won't get a response to they won't get a chance to respond to it, or they'll just have to kill the cells. That's another.
Yeah, so I think the starting place, they just need to do people just need to do low dose experiments because it's a binary thing where a cell gets hit or it doesn't get hit. It doesn't get hit twice by heavy ion. It'd be really rare. It's just Poisson distribution, the probability that an iron particle or one of these heavy ions goes through a typical cell twice is negligible. So they need to do the experiments at a low enough dose where it gets hit or it doesn't get hit. And then if it's in the tissue, you can study this non-targeted effect as the hit cell sends signals to the non-hit cells. So the problem is that a lot of people use higher doses where they're getting hit several times or maybe 10 times. I mean 10 different heavy ions go through the same cell, which is just something that doesn't happen in space. So you don't really need to do chronic. You just need to use low dose. Now the exception would be if in the chronic exposure, the whole tissue is changing as the exposure goes on. So there's not a lot of evidence for that, but I think really the starting point is just to use a low enough dose and several low doses where not all the cells are getting hit. And then that should be good enough.
Astronaut that died of cancer, this kind of gruesome question, I guess. Did they do an autopsy on them to see some of them?
Yeah, so there's something called the Longitudinal Study of Astronaut Health, where all the astronauts active and then retired are invited to come for annual exams. The retired ones usually come at least every 2 years. And so they track all their cancers, and then when they die, they're in contact with the families to see if their autopsy reports would be sent in. So there's been about 14 cancer deaths. That's all public record, and then maybe three times cancers. That's not in the public record, but there's some reports that give you the numbers. So they've done them, but what they do, that information is not really driven by radiation or looking at it from that point of view. Okay.
I just have one more question about the CNS impairment. So it's clear how you can get the chronic effects, but I'm wondering what's the main mechanism for the kind of hypothetical acute impairment, where you would have it during the mission. You mentioned the severing of dendrites that can happen, so I could imagine that can affect someone's cognitive abilities, but what else would actually...
Oh, so the impaired neurogenesis is one, and then the morphological changes. You do see the persistent ROS and inflammation. But that's kind of foggy, and it's important, but what's the mechanism is they don't really know. There's other things that can change the morphology, so like stress, there's certain, but it's interesting because in mice, they know these things in a lot of detail, like this is the first layer of neuron, the second layer of neurons, and where do they communicate with. And so with stress, they call the CA3 neurons are degraded by stress. And with radiation, it seems to be nonspecific. So that's something we're pursuing as if it's energy deposition and ionization, it shouldn't be very specific to the type of neuron. So that would be how we're looking at whether it's from the radiation or is it a non-targeted CNS effect where you stress the animal out and that causes their neurons to degrade. And there's other things like that, hormone changes and other things that will occur that will also degrade your neurons. So they,
Biology changes actually
yeah.
have an effect in the short term?
Oh yeah, they do, yeah. Because you're changing all the circuits and all. And the other one is, you do know, so neuroinflammation is kind of broad, but the one thing is activated microglia cells. You know that they'll attack the spines. And then, so that your spine density will go down. One of the theories we're pursuing is if you have a series of these loss of spines, does the dendrite then get reduced because it's kind of dead at that point? So we said, but which comes first? We don't know. That's the things we're looking at. Yeah. Okay.
Clarification. What I understand, so previously commented, you say that the current kind of like shielding and construction of spacecraft now is sufficient and good as it relates to solar radiation, but not cosmic radiation. And that's where the risk management comes in. You feel that is also applies, say if there were a mission to Mars in an extended time period on the surface, do you feel that shielding would come into play on the surface if there was an extended 12-month, 18-month time period? On the surface of Mars.
So on the surface, you have the you have the terrain, which can help. Like if you locate a habitat next to a cliff, there's tunnels you could make, but then you're a mole. Why bother going if you're down in the tunnel all the time? But it's harder to shield on the surface because you've cut down the atmosphere. The atmosphere has cut down lower energy particles. So shielding always works for the lower energy particles. So you've gotten rid of more of those because of the atmosphere. So the higher energy particles are more difficult to shield. So I think it plays less of a role. And then you also have the confounder about the soil. That there's predictions that some areas where you have the higher Z soils, like iron and silicon in the soil, you'll get more neutrons up. So you can that's sort of related to the shielding problem. Yeah.
So in that regard, what's worse, a neutron or an iron particle? So it seems like I would trade a neutron or an iron particle for a neutron. So long as
It depends on the energy of the neutron. I think like a half MeV neutron is worse than a heavy ion. But a 2 MeV neutron is less biologically damaging than an iron particle. So there's a sweet spot with the neutrons, and that's because the protons. So the protons are, when you make a proton that's like around a half MeV proton, it's really damaging. So you have to make it in the cell because it doesn't penetrate. So if a neutron comes in and gets into your cell and makes a half MeV proton, that's going to cause a lot of DNA damage, more than an iron particle in that cell. So, but the other thing about the iron particle, it's making a column of damage through the tissue. So in some sense, it's more damaging. Yeah. Okay, that seems like enough questions. Thank you very much. Yeah. Okay.